Second speaker this afternoon is Larry So, who will talk about weighted polyhedral products.
Yes, okay. Thank you, Stephen. And first of all, I'd like to thank the organizer for inviting me to give a talk here. So today I'm going to speak about my joint work with Don and Stephen, where we construct a new family of spaces that generalize the notion of polyhedral products. Okay, so first, I know that everyone here is an expert of polyhedral products and know the definition very well, but still I want to quickly remind the definitions and the constructions of polyhedral products to set the notations. So first of all, remember, when we define a polyhedral product, we need two inputs. So the first one is we need a simplicial complex K on endpoints that encodes all the combinatorial informations on how we glue things together to construct a polyhedral product. And the second input is a sequence of pair of spaces sequence of pairs of spaces. In particular, when I mean the pair of spaces, I mean that for each AI is a subspace in Xi. Okay, then probably I want to stick in this board. Okay, and then how do we construct a polyhedral product? So we need two steps. So step one, so first we define the polyhedral product with respect to each simplex in K. Sigma in K, we just define corresponding polyhedral product to be a product of spaces y1, y2, and so on. Everyone knows that very well. So where the space yi is taken to be xi, depending on whether I is contained in sigma or not. Otherwise, we just take yi to be ai. And if we define this way, then the good things about this is if we have another simplex tau, which is a subsimplex of our sigma, then the inclusions of this simplices from tau to sigma will induce a space inclusions from the polyhedral product of tau to the polyhedral product of sigma. And then using these inclusions, we can just define the polyhedral products with respect to K by taking the unions of all these polyhedral products with respect to all simplices in K. But at the same time, as you have heard this many, many times, another way to think about this union, you can also think it as follows. You can think about the polyhedral product as a functor from the poset category of K to the topological space. And this one, you can think it as the colimit of this of all the polyhedral products of sigma, and then try to do the colimit for running through all the sigmas in K. Okay, everyone knows that very well, but later on we will try to modify this to construct some new spaces. But before that, let me give an easy example as well as motivations of our constructions. So I just take our pair of spaces to be just some spheres and points, then if we look at the polyhedral products of XA corresponding to a full simplex on M points, and then everyone knows that it will be just the product of spheres, Sn1 times Sn2 times up to Sn over M. And now if we take the homology of this guy, by Cooney theorems, we know that the right-hand side will be just the tensor product of all the homology of spheres, and it turns out to be an exterior algebra on M generator. And where the degree of the generator xi just equals to the dimension ni of the corresponding sphere. And in fact, we can also look at this exterior algebra as a graded modules. Then you can write it as a direct sum of three abelian groups generated by products of the generators. And for example, so here, you just take the direct sum of all these three abelian groups for all these subsets in bracket M. Okay. This is this isomorphism as modules. So that's the two. Okay. Then now, one of our motivations of our project in the beginning is we want to study a special case of a realization problems of algebras. So what is a realization problem is as follows. In algebraic topology, if we are given a space, then we can take its cohomology. Then we know that the cohomology range is a graded commutative algebra. So the realization problems ask about the converse. So if we are given a graded commutative algebras, can we find a space such that its cohomology range equals to this algebra? And the motivation of our project is trying to look at a family of algebra that looks like exterior algebra and try to see whether we can realize them. So we want to modify the exterior algebra to define a new algebra as follows. So first of all, we just take our new algebra to be a direct sum of three abelian groups as if before. So we just take it to be a direct sum of all the three abelian groups generated by some generator, let's call it Y sigma, where sigma is some subset in bracket M, such that the degree of Y sigma equals to n sub I1 plus n sub I2 and so on, and sub Ik, where if sigma equals to the subset I1, I2, up to Ik. So essentially, as a modules, then it is just the same as the exterior algebra, but we want to change the multiplications on this algebra as follows. So if I have if I try to multiply a bunch of generators yi1 times iy2 up to so on. So in the exterior algebra case, this guy will be just equals to I sub y sub I1, I2, and so on, ik. But now we want to modify these multiplications by adding a coefficients. Let's do it by c, I1, I2, and so on. This is some coefficients. And of course, we have to pose some conditions on these collections of coefficients in order to make these multiplications a well-defined ones. So we have to require the set of coefficients to satisfy some conditions. Namely, we want to make sure that C empty set equals to C correspond to any one point will be equals to 1. And second, if we have a subset tau inside another subset sigma, then we have to make sure that C tau divides C sigma. And in fact, posing these two conditions, you can make sure that this will define a new algebra. And how about let's call this new algebra to be a lambda C M here. Okay. So the motivation of our project is to explore the following questions. So for which algebra, for which collections C, the corresponding algebra lambda C M is realizable. Okay. For example, if you take all the coefficients C to be equals 1, then the algebra will just recover the usual exterior algebra. And we see that this is just the cohomology of the product of sphere. Of course, is realizable. And we'll try to do some easy case. For example, when m equals 1, then this algebra is always a ordinary exterior algebra, and of course this is realizable. And similarly, when m equals 2, it's not difficult to construct a realization space, and of course this is also realizable. For m equals 3, when you try to construct a realization space, it involves some hard calculations, but posing some conditions on the dimensions and also the degrees, then it's still realizable. But when m is greater than or equals 4, our methods doesn't work anymore. One reason is because we try to construct a new realizations by using the previous realization space, but when we do it in the previous steps, it involves some choice of the homotopy types of the, or homotopy class of the attaching map of cells. So when you try to put it together in a higher m cases, you have to make sure these choices, they have to be coherent or compatible with each other, and this becomes difficult when m gets higher. So, in general, we don't know how to construct a realization space for m is greater than or equals 4. So what we do is like we impose a combinatorial, yes? Yeah. You can't just, that has to be part of the condition. For example, I mean, if Don is pointing out that exterior algebra has an even sphere in there. Yeah. Then the even generator would have to commute on that to commute with any other generator. Yeah, but I'm not sure whether I mean, like when we, I mean the compatibility, I'm not talking about, I'm not sure like the commutativity will ensure this, coherence of choice of the attaching map, but maybe I can talk to you later. Okay. Okay. So, but what we do is back to this story here. Like, what we do is that we try to pose a conditions on the set of coefficients in order to construct realization spaces that solve the problems. But later on, we realized that we can extend our constructions. Then then it generalized the notion of polyhedral products. So that is why we construct these weighted polyhedral product things. Okay, this is just an introduction for our constructions. Okay, the next one is now I talk about the constructions of the weighted polyhedral products. Okay, so the slogan is when we construct the weighted polyhedral products, we try to do it inductively by adding cells together. But when we adding cells, we always precompose by some degree maps in order to construct something new. Okay, so let's go back to the previous board. So we try to modify the definitions of a polyhedral product. In the ordinary polyhedral products, we need two inputs. But in our constructions, we will need three inputs. First, we need a simplicial complex case to encode all the combinatorial informations of how to glue things together as before. And the second input is still we need a sequence of pair of spaces. But now, because we want to precompose some maps like degree maps on these spaces, so we have more, we have extra assumptions on this pair of spaces. And we want them to have some self-map that looks like a degree maps or a power maps. And we call this kind of pair of spaces a power couples, which I'm going to explain it in a minute. And third input is at the same time to ensure the coherence of all the degree maps. Then we also need a notion, what we call a power sequence, which is a map, let me denote by gamma, is sending all the subsets in, let's say, the full simplex in m-1, something like that, or plus 1, the full simplex on m points to a m tuples of positive integers that satisfies certain conditions. That we need this one to ensure some coherency issues that I'm going to explain it later as well. But in the end, like the overall picture is like now we modify the inputs parameters, and then we try to construct the weighted polyhedral products, same as before, but like with some modifications. And now I'm going to talk about this. But first, let me explain this notions of power couples and also like the power sequence. Okay. Then maybe I'll just go back to here. So the definitions, first of all, I would define what is a power couples. As I said, we want a pair of space, let's say XA. We call it a power couples if for each natural number A, there exists a self-map, what we call a power map. Let me denote by rho sub A. It's a map from X to X itself, and they satisfy two things. First, for rho sub 1, we want it to be the identity map. And second, we want, when we compose two power maps, rho A compose it with rho B, then it will becomes rho sub A times B, and no, there's no third conditions. Sorry, yes, yeah, that's enough. So essentially, the motivations of a power map is just a power map of topological monoids. So let me give you some examples of power couples. Okay, I still want to use this one, so maybe I'll just clean this board. So for example, first example, like if I have any pairs of spaces, we can consider it as a power couples by equipping the trivial power maps. Oh, sorry, I remember. Sorry. Yeah, yes, sorry, yeah, I remember the third condition. I remember there are three conditions, but I just can't remember. Yeah, sorry. The third condition is you have to make sure that the inclusion of A into X is compatible with the power maps, yes. So you can express this condition by these commutative diagrams here. Yes, back to the examples. So if I take any pair of spaces, XA, you can equip it with the trivial power maps. Namely, for any rho A, it's just the identity map. Okay. Secondly, the pair of the circles and the points is a power couples, where the power maps rho A is S1 to S1. It just sends EI theta to EIA theta. So this is the degree A map, or if you, it's also an A power maps if you think of S1 as a unit circle in the complex plane. And from this, using this power maps, we can also make suspension X, comma point, power couples, where you just send the pair EI theta X to EIA theta X. And therefore, it makes any pairs of a sphere and a point is also a power couples. Okay, there are also other examples, but I'm not going to talk about it. I want to save some time for the rest of the talk. And okay, now I have the notions of power couples, and now I also need to talk about the power sequence. Is just a power couples. Sorry, power sequence. Let's say gamma is just a maps from the minus 1. Okay, from the subset of the full simplex to a n tuples of positive integers. And for example, let's say I just send a sigma, and then it equals to some n tuples of positive integer, let's say rho gamma 1, sigma gamma 2, sigma, and so on, gamma m sigma. And then we want these coordinates to satisfy certain the following conditions. First one, we want, let's say, c I sigma to be equals 1 whenever I is not contained in sigma, and, gamma. And second condition is whenever I have a subset tau contained inside in another subset sigma, then I want my gamma I tau to divide the gamma I sigma for all I. So we post these conditions, then it will help us to essentially this power sequence just tells us what power maps we should apply to each spaces in our inductive constructions. And this data just help us to ensure that these degree maps are compatible with each other. Okay, now, after I talk about the 3 inputs, and then now we try to define a weighted polyhedral product. Again, like we try to, first we define weighted polyhedral product for each simplex first. But we are in the usual polyhedral products, it is just defined as a product of space, and that is easy. But in our weighted versions, then we need to construct it inductively by adding cells to the previous constructions. So this is more complicated. So I just cross this, and then goes to star here, and the star is so we defined the weighted polyhedral products as follows, or so for each simplex sigma in M, then there exists, okay, sorry, I should say in this way. There exists a collection of spaces we denote by XA dot gamma, where dot can be any simplex sigma, or it can be the boundary of sigma, and a collection of maps that we denote by eta dot. This is a map sending from the ordinary polyhedral product to the weighted version one, gamma, where dot can be sigma or boundary sigma. And they satisfy the following properties. And of course, these spaces, we call it a weighted polyhedral product. First, when sigma is just the empty set, then we define it to be the same as the ordinary polyhedral products. So namely, it's just the product of A1, A2, and so on. And in this case, we just define the comparison map eta to be the identity map. And then second, later on, then we just define the, let's say, the weighted polyhedral product with respect to, let's say, vertex 1, gamma, using this push-out diagram. Here, like, you try to, for this map, you try to apply the product of the degree power maps given by the power sequence, gamma 1, 1 times gamma 2, 1, and so on. And then you form the push out, and you call this the weighted polyhedral products with respect to the vertex 1, and this map will be the eta 1. And this is to ensure you add this power maps here to ensure that you got something new here. And of course, you just define the weighted polyhedral products for any single vertex in a similar way. And then thirdly, then you just defined for any sigma that has cardinality greater than 1, you just defined the weighted polyhedral product with respect to its boundary sigma to be all the colimits that of the weighted polyhedral product with respect to tau, where tau are all the simplices contained in boundary sigma. And then you also defined the comparison map to be the colimits of tau, where you compose the eta maps on tau by some power maps here that is indicated by the power sequence. And then you can check that this is well defined, and eventually, okay, how to eventually? Eventually, I should use this one. So eventually, you just form the weighted polyhedral products using this push out. And this is the eta sigma. And then you can check that like all these constructions are well defined. Okay, example. First, suppose that when X and A are just any pair of spaces that is equipped with the trivial power maps, then in this case, the weighted polyhedral product is the same. Oh, sorry. After that, again, you go back to the step 2, and then you just define the weighted polyhedral product to be all the colimits of the weighted polyhedral product of sigma. Okay, sorry. Back to the examples. So when your pair X and A are just any pair of spaces with trivial power maps, then you can think of it as power couples, and you will get a weighted polyhedral product, and that will be the same as the usual one. Or when XA has trivial power maps. Or another case is, let's say, when the power sequence sigma is trivial in the sense that we just send everything to n tuples of 1, then the resulting weighted polyhedral product is still is the same as the usual one. Okay. And next one, let's say now I take M to be 1, and then my power sequence of 1 would be just equals to, let's say it's just gamma. Then if I look at the, okay, and then I take K to be just 1. Then if I look at this with a circle, then the 1 vertex comma this gamma, it will either equals to a disk when gamma is 1, or it will be a Moore space, a mod gamma Moore space when gamma is not equals 1. So you obtain something new. And but let's say if I look at the complex plane and the puncture complex plane C star, then you can show that this is just the complex plane quotients, the discrete group of order gamma, and homomorphically, this is just the complex plane, so which is contractible. So you see that this weighted polyhedral product is not equal to this one, even up to homotopy. You should compare this result with the usual polyhedral products, where we know that D2S1 for any simplex is always homotopy equivalent to C star with the same simplex. Okay, so we think something new. Okay, now we construct something new, and at the same time, we know a lot of properties about the polyhedral products. Then the next question is whether these properties also hold for the weighted version one. So because of the time, maybe I just talk about the stable splittings. So recall that in the usual polyhedral products, let's say I have X A, where A's are all points. So if we take the suspensions of these polyhedral products, then there will be a homotopy equivalence between a wedge of all the suspension of its polyhedral smash product. I think something like this. I can't remember the K sigma or something like that. Okay, this is something K. And this guy, what is this? In this case, I just give the simplest version. So this is just equals to the xi1 smash xi2 smash up to xik, where I1, I2 up to ik is our simplex here. And in fact, this is also true for the weighted polyhedral products. We obtain a similar result, that we obtain a homotopy equivalence between if all the subspace are just a point, then we're able to obtain a homotopy equivalence between the suspension of the weighted polyhedral product and the wedge of these smash products things. And of course, you want to compare this stable splitting of the weighted polyhedral product and the original ones. If we impose another conditions that, let's say, if all the xi are suspensions, let's say, and the power maps comes from these suspension coordinates, that is, I have written in the previous example, then we can compare the two stable splittings in the following sense. I think like here we're only able to do a sigma, a direct sum of h star of this x comma point tau sitting in the sigma, and then we, with the eta maps, star h. And direct sum of some, let's say, capital gamma tau here. And this capital gamma tau is just a multiplication maps on the pieces of the x corresponding to tau to itself, x comma point tau, where it sends x to some numbers given by the power sequence. So you see that, like, because of this, the weighted version of the stable splitting can't be the original one. Okay, and then like 3 minutes to go. And another property that I want to talk about is the cohomology ring. So recall the following result of polyhedral products. So assume that for each cohomology of xi is torsion-free, then we can identify the polyhedral products of x comma point k to be equals to the quotient ring of x comma point with respect to the full subcomplex divided by this generalized standing rising ring here. This guy is actually equals to the tensor product of all the xi and for this ik things, this is generalized standing rising ideal. So and this is generated by all the monomials xi1, xik, such that each xij belongs to some elements inside xij. And at the same time, here we have the set I1, I2, up to ik is not contained in K. So our result is similar to this known fact. Suppose that if all the xi has cohomology torsion-free, which is torsion-free, then we also need one more condition that suppose all the xi is a suspension, and the power maps comes from the suspension coordinates, then we obtain a similar result. That is the polyhedral product of x comma point with respect to k gamma is the quotient ring of this guy. And of course, this guy is not a tensor product of all these cohomology rings, but as a module it is, but you just have a more complicated multiplication structure. And then in this sense, you can also talk about this generalized standing Reisner ideal, then we get the same thing here. And in particular, we know what is this guy in the special case when all the x is just sphere. Okay, I think I'm running out of time, but I'm going to talk about this. Then I will finish. In particular, when all the xi is just a sphere, then what is this guy? This is just equals to the weighted version of the standing Reisner, sorry, the weighted versions of the exterior algebra quoted out by the generalized standing Reisner ring. And this C, what is this C? Actually, this C is induced by our power sequence. And this is equals to, you multiply all the coordinates of gamma corresponding to sigma, up to a gamma sigma. And one corollary is that when you take K to be the full simplex with endpoints, then it says that this cohomology ring is just equal to our new algebra. So in particular, this algebra is realizable in this case. I think I should stop here now, and thank you for listening.
Are there any questions?
So is there any reason you want to realize those exterior algebra? So what can we do with it?
Oh, it's just a special case of the realization problem, because you know that the realization problem is very difficult, and somehow, okay, like for the integer case, very little unknown about the realization problem. So we're just looking at the family of algebra that looks like exterior algebra, and so that we're able to say something about whether we can realize them or not. So yeah, it's just we want to study a special case about the realization problems.
So in the first slide, you mentioned that for m equals to 1, 2, 3, those are realizable with classical polyhedral product. Is that right?
We're able to construct a realization space.
But not always using polyhedral product.
I think we have some other easier methods. But I think we use the polyhedral product because we want to construct with the realization space inductively. So we want to do it, that like categorically, so that we can ensure the coherency of the choice of the degree map, something like that.
Okay.
Are there any other questions?
Could you put a different, I mean, presumably you've, on an exterior algebra, the, say over field of characteristic P, the Steenrod algebra is acting trivially. There aren't any Steenrod operations. I mean, I'm presuming there aren't on your thing has trivial Steenrod operations as well. Might there be a, could you visualize an exterior algebra where you've twisted it by putting a Steenrod algebra operation somewhere, and maybe there's no...
Yeah, I think like it's good questions. I think this can be one of the directions that we can try to look at this problem. Yes. But I think like yes, we can also look at the steer-on operator on this thing and how it generalizes this result. Yeah.
Thank you.
Any other questions?
Just related to Ian's question. So can you tell us what really are the summands in this table splitting for the weighted case?
Oh, it's the same one. It's just the same wedges as the usual case, but
So why is then your cohomology different?
yeah, it's because if they are the same, then probably it just implies that this weighted polyhedral product is equals to the ordinary one, but it's not. I mean, like, we have a stable splitting for the ordinary polyhedral products.
Yeah.
And there's also one in this special case, x comma points for the weighted versions. And all the wedge edges are the same, but the homotopy equivalence can't be, but there is no homotopy equivalence between the weighted version and the ordinary versions. So that's why, yeah, that's all I want to say.
Okay, thanks.
I'm not sure.
Any other questions? If not, then I think we should thank Larry again.
Okay, thank you.